Welcome to EDU World Space.
We will be deriving the Compton scattering relationship that relates the shift in the wavelength of the photon after its collision with an electron as a function of the outgoing angle of the photon. So the diagram below shows the collision, which we can treat with the usual collision quantities. And in particular, what we want to note is that this is an elastic collision, which means that it will get to conserve both energy and momentum. So those are the two relationships that we want to write down: conservation of energy and conservation of momentum. And working with those, we can hopefully come up with that relationship. Now, it is kind of tricky because we do need to use relativistic relationships. So we'll do conservation of energy on one side and momentum on the other. And then we'll see what we can do with the various equations to come up with an overall equation for the angle and the shift in the wavelength. Okay, so let's just kind of write down the incoming photon has an energy coming in, and it has a momentum which is related to the energy just through the speed of light. So that is a relativistic relationship. And the same with the outgoing photon. It has its own energy and its own momentum outgoing. I should say photon, PH for photon, not PC. There is a speed of light in there, but not as a subscript to identify the photon. The electron, if we are considering relativistic energy momentum, it starts off with rest energy. And of course, we're going to assume that it's just sitting there, so no initial momentum. And after the collision, it has a new energy, which we use with our relativistic formula that relates the addition of momentum and rest energy to come up with the new energy. And the momentum is just m times gamma times v. Okay, so you can see that it could get a little bit hairy. And we know how to write the energy of the photons in terms of the wavelengths, but we'll not worry about that until we get to the end. So this is the easy part, is just writing down conservation of energy. So on one side, I usually like to put the initial, and same with my momentum. We have another situation with momentum that we'll get to in a little bit, namely the two components. And we'll kind of break them up. But anyway, here's our energy. We start off with the energy of the photon plus me c squared. The rest mass of the electron has to equate to the energy at the end. And usually you do not want the square root to hang around. So there is a trick you use to get rid of that square root, which is to cluster everything on one side of the equation without the square root, and then to square both sides. So I'll just kind of show schematically how that works. And this is where the real fun starts to come into play. You can see where the fun comes into play. Okay, and we'll get rid of the square root. Okay, so square both sides after square root is isolated is the trick. Okay, it almost takes as much to write the trick down as it is to do the trick. And you can see that we have kind of a messy, what do you call it? Trinomial, but we're going to keep it as a binomial for now. So we'll go ahead and expand out the binomial. On the left-hand side. And that's where things are going to get a little bit messy, but we will take it in steps. But yeah, this is where your algebra comes into some help. And even being good in algebra, you can mess this up. So we'll be as careful as we can. The last term on the expansion is going to cancel. I'll just show you when you square this, it will cancel the MEC squared on the other side. So I'll kind of just skip that step. Probably not worth writing. Okay, and that's where I'll quit with that to look at the momentum. All right, momentum conservation. What we know about momentum conservation is that we are going to have both an x component that gets conserved and a y component. So let's do the x component first. Oh, let me find a different color so I don't get that purple. So we have the initial momentum of the photon is equal to its final x component, which goes as cosine theta, plus the momentum of the electron, cosine of alpha. And we have a similar type of relationship for the y component. Okay, none to begin with, and then the two particles afterwards have the parts of the y canceling. Okay, now here's a note, is that really you do not want alpha in there. So alpha is the angle the electron makes, and there is no way to observe this. So what we're going to try to do is use those two equations to eliminate the alpha. And there's a trick to do that. It's an algebra trick. But you basically want to isolate the cosine term in one equation. So you'll kind of see how this works. It's kind of a nice little trick that oftentimes works in even mechanics with harmonic oscillators and things that have cosines and sines in them. But you then want to also isolate the sine. And then what you want to do is square both of these equations. And what will happen is on the right-hand side, you'll have cosine squared plus sine squared equal to 1. And so the alpha will just kind of go away. And I don't want to show you all the messy algebra. I will just show you the result, which you could verify with a little bit of algebraic manipulations. Yeah, and it's starting to look like a mess, but we'll see. It's not quite as bad as you think it may look. Okay, we say. So hopefully you can see how that works. Okay, and again, you can have some algebra fun squaring out your relationships. But we'll do that in a little bit, because the next thing you can see is that there's kind of a correspondence between these two equations. On the right-hand side of both of those, you have something that looks like a c squared. And so the next step is to use the transitive property, is to multiply the conservation of momentum by c squared on both sides, or alternatively, you could divide the energy relationship by c squared. Your pick. And I may actually want to divide the energy by c squared. Yeah, I think I want to do that. It really doesn't matter, but I like to be consistent. So we'll divide both sides on my energy relationship by c squared. And then by transitive property, we are going to equate the two. Okay. And we're going to expand out the binomials in each of those. So that's our next step, is equate, what to call this, equation 2 has sort of transmogrified into this thing. Okay, equate left-hand sides of 1 to equal 2. Expand out the binomials. And yeah, that may sound very scary, but let's kind of do that carefully. And you'll see that a lot of things are going to cancel. And the reason being is that the energy of a photon divided by c is the same as its momentum. So let's kind of do that. So we're expanding out our equation 1. That would be helpful if I wrote it down, but let's minus 2. Okay, so I've just expanded out the binomial. Let's see, there's a plus 2. Okay, so that's the left-hand side from equation 1. And now let's do the same with equation 2. And we can see that we can actually, I think I have something in there wrong. I should have a square on that term. Yeah. With the sign squared in there, that p photon should also be squared. Yeah. Okay. Now I feel better. Okay, doesn't pay to go too quickly through this, or mistakes can be made. Okay, I'll just show that as a correction. And now what I want to do is to equate that the energy divided by the c is basically the photon momentum. So I can start to simplify the sides. The first term is the momentum squared of the photon before it collides. And same with the second term. Okay. Okay, and leave one factor of c in there. And we can see that there are going to be a lot of goodies that cancel. So one thing I can do is use the cosine squared plus sine squared gives us 1. Okay. So now this is where the fun comes in with lots of cancellations from left to right. And I managed to keep myself fairly organized. And so I can see, factor of 2 is going to disappear. And what I'm going to be left with is I'm going to carry this to the opposite side. Let me see, we'll carry this to the opposite side. And what we'll be left with is the photon momentum difference times MEC squared. MEC, pardon. We used one of the C's already, is p photon prime, times 1 minus cosine theta. Okay, and it's not too far after this. I will just summarize the rest of the algebra. But by inverting this equation, so we want to finally invert the equation and use the fact that the momentum of a photon is the same as h over lambda. And you will wind up with the final equation. It is a little bit more algebra, but at this point it's sort of more straightforward to finagle with the inverses and cross multiplying. But you can see where the structure is coming from. The wavelength difference is going to come from here. The 1 minus cosine theta is going to come from there. The HME times C is going to come from definition of wavelength and that MEC. So, yep. Okay, so that's the shift in the wavelength due to the Compton effect. And one nice way to purport this constant out in front is you could leave it in the form of HC over MEC squared. And then you're talking about using the 1240 EV nanometer cluster of constants divided by the rest mass of your free particle, here the electron, to come up with the so-called Compton wavelength, which is a scaling factor, more or less, that tells you of the order of how big that wavelength shift could get. Depending on the angle, of course, it will be different, but gives you an order of magnitude.